You guys said you wanted it horizontally oriented, which means who would have come first in the standard form, an X or a Y? An X. An X. Okay. Let's see, let's make them about the same distance apart. Let's make them about the same curvature, but I want it pretty curvy. Once again, we're not going to have the arrows going on forever and ever, because a real shape would not go on forever and ever. Those look pretty similar, right? Okay. Since I have a smartboard, I'm going to do boop, boop. That didn't work. Boop. There we go. Transverse. What did I have you guys write next to transverse? Through. Good. Through the curves. So which axis goes through the curves, guys? Horizontal or vertical? Horizontal. Horizontal. So if I'm revolving around, in this case, the horizontal, I'm going to extend him just a little bit, just to make it easier to see. We always have to put that revolution arrow, right? Showing the revolution. Where's the spin happening? Where are your fingers holding and spinning? So if that's the transverse axis, super important, there's a special name for it and everything. That's going to be important for the test. Who must be the conjugate? Well, it's the one that doesn't go through, right? So if it's not the horizontal, it must be the... This one is interesting. Guys, if this hyperbola only had one parabola, does that make sense? If this hyperbola had only one parabola, that's one way of looking at it, and I was spinning it around its transverse, which is what I'm holding right now, right? If I was spinning it around its transverse, question, wouldn't it be like the axis of symmetry? Yeah. And if it would be like the axis of symmetry, what was formed when we were spinning it around the axis of symmetry for a parabola? A bowl or a cup, right? So how many do I have now? Two. They're doing their own thing. They're in their own little world. Each branch is just doing its own spinny spin, spin, spin. So therefore, you can just make two cups or two bowls, or in a sense, two paraboloids. Now, it's called a hyperboloid. Technically, hyperbolas have asymptotes, parabolas don't, so that's a little bit different in that these aren't truly kind of look like it. Do you guys see your two bowls or your two cups? Hey, and it's called what? A two sheet. Oh. Like you kind of need like two different pieces of material, two sheets or two solids or two blocks of wood to make this. You can't just do it in one. They're two totally separate figures, totally separate solids, but related together, mathematically speaking. Two sheets. Way of representing it. But who's this guy?
One sheet.
Huh. Jason, what were you about to say?
Is that how they're going to refer to this homework, like a two-sheet?
Maybe. Or maybe that's just the way that I'm going to ask you to name it on the test. I actually don't remember. Did they name it in homework? Prolate, oblate, one sheet, two sheet? I don't know. I think they just say form the hyperboloid and they make you figure it out, I think. Okay, now here's the struggle. This is the axis that goes through. True?
Yeah.
So what if I have to go about the conjugate axis? I can't rotate it this way because those are the two separate bowls, right? So maybe somehow instead, I should have brought the tape up and I didn't. I have to go the other way. Can you guys visualize and try to think of if you were spinning what it would make? Not like a donut. Like a what?
Oh yeah, the little like weather.
That's more similar. Try to draw it. Try to draw it. Oh, come on, you're fine.
It's like a future reactor.
Or just that line? Like
They're spinning. An hourglass. An hourglass? An hourglass, huh?
A way to think of it would be like if you took an hourglass and set it on its side and played spin the bottle. That would be like how it's going to be.
Look at Jason being a student. Oh, you guys sound so smart right now, even just trying to describe it. Multi-dimensional. You can tell that Wrinkle in Time came out as a movie in your generation. Wrinkle in Time came out as a book in my generation. My sister's technically. You guys ready? Probably can't see it though. That's the hard part. Because the weird thing is, do you guys, well, first of all, those strings are way too distracting. The weird thing is what was made solid before, guys, wasn't when we were spinning the other way. When we were spinning the other way, wasn't the solid in here, like where this is, right? The weird thing is the solid isn't in here anymore. The solid's actually in the middle. So what you have to visualize is the space in between, and that's what gets really weird. Now, some of you are thinking, I think, like the weather vane, like the cup's going around, but the weird thing is it's actually not here. It's in the middle instead when you spin it. And it's really hard to show you without going really, really fast. I can almost do it. See, this is what I need. I need little thingies to hold, and I can like zoom, zoom, zoom. But I can't.
Is it like a wheel without the tire? So it's like a circle.
Yeah, it is. You ready? How is this a donut? It's an hourglass, you weirdos.
Wow. Look, I said donut. If you covered the outside, it would literally be a donut.
Or an old school spool of thread. Or like the tire, what would you call it? Rim?
Yeah.
It's the wheel. Well, the wheel's the, yeah, because the tire is the, that's confusing. Yeah. You know what I'm talking about, though. Yeah.
It was an hourglass.
Because here, the solid's being formed inside the parabolas. Here, the solid's actually being formed by the outer shell of the parabolas. Yeah, kind of. Kind of. Like the Potter wheel. Look at you guys. You were paying attention in chapel. At least to what he was doing. Chapel, the Potter's wheel. The Potter? When she came? Oh, sorry. Mr. Hogan did it a few years ago. That was the he. Yes, she came this year.
This year?
Were you gone? That was a cool one. Yeah.
I've been gone a lot.
The Potter was up on the stage. When Mr. Hogan did it, and he was the old Mr. Horn, they had like a video camera zoomed in. Riser, the old Mrs. Marquez, the art teacher, she was like talking through the illustration of, anyway, it was cool. Technically, just the parabola is spinning. And technically here, just the parabola was spinning, but it was spinning in a way that it formed the shape inside. Here, it's spinning in a way that it's forming the shape inside.
You just said inside twice.
Yeah, but do you see how the insides were different? This one was towards the conjugate, and this one was towards the transverse. Anyway. Yeah, I don't think either of these are as complicated as the ellipsoids as far as drawing. But do you have to know who's who and what's what in order to draw it?
Yes.
Yeah. But do you see why this is just a one sheet? It's just one figure. Two came, well, when this guy goes around, he's going to actually collide with that guy. That guy's going to collide with this guy. It's really just one figure being formed in tandem by the two different branches. These, though, were totally separate. So you have the two bowls, the two sheets, the two sheet hyperboloid. You have the one figure, or the one hourglass, or the one sheet. Now, my non-artistic ones, I think you kind of got it, hopefully. But this one, couldn't you like zoom, and then like boop, boop, be like, yay, two bowls. It's kind of gross, but yeah. And then down, okay, maybe you can at least connect them. You can at least connect them. That's even worse. This one, can't you just like spin it and spin it? 1, 2. I can tell the difference. Can you? Can you at least draw the difference? I hope so. Okay, zoom, 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 zoom. That was my rotation arrow. Zoom, 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 zoom. Okay. So let's go ahead and check out what homework is asking of you additionally. Some of you were able to do some of it last night. Some of you weren't. Here's the dealio. They're going to say, spin him. You can't spin him until you get him. Don't you have to draw him first? But is it as hard as, I mean, we could go ahead and rearrange him, right? We could get the standard form, move x squared to this side, and then move y to this side. Then we could go ahead and do like an x minus 0 squared, but then we're going to have to figure out, well, what do we pull out? I guess we could pull out a -1, and then we'd have a y minus 9. Then we could make this equal to 4p. Like, we could do the focus and the directrix and get the standard form and review section 10.2. But don't we know what this guy looks like? Because you can actually use old school math without having to get the vertex this way, 0, 9, to say, oh, isn't he this guy gone up 9 and flipped down? So sometimes you can cheat a little bit from old math that you know to say, like, he's 9 up, he's concave down, and we could even be super snazzy and say, when is he going to hit the axis so I can be super nice and precise? At equals plus or minus 3. So I can go 3-ish. Now we also have to be able to read the directions because they're saying something like, oh, we have to cut him down. We can't just say go on forever. So they say revolve the part of the graph. So part of it's learning how to read directions and see what they're saying. That lies in the first quadrant. Well, guys, if I make this parabola, first quadrant, isn't that only this piece? Because that would be second quadrant, that would be third, that would be fourth. But what are they having me do with this piece? Where or about what? The y-axis. So where do you put your rotation arrow? Y-axis. Yeah. Then in your brain, hopefully you're having your brain be like, oh, hey, spin. So my hands would be this way, and I'd be spinning, right? And as I spin, wouldn't he come out? Oh, this is weird. They say only take him, but if I spin him, where's he going to go?
Hit the -3.
Isn't he going to hit, like, isn't he going to come around and make that side? So really, I can just draw my paraboloid like this. Cut off boiled egg? I don't really know how to answer that. Okay. Otherwise known as a paraboloid. Yay, go team. Anyway, so this one was a little bit easier because it's like, oh, hey, it's an x squared. Take it up 9, flip it down, and then spin it. Paraboloid. Ta-da! But is the next one going to be as easy? Now pause. Questions on this one? Do paraboloids have different names, or is it just paraboloid?
Wait.
Because there's only one axis, we'll spin it around. Okay. But how about this guy? How do we graph him?
It's a 2 squared and it's a negative, so it's like.
Okay, Joe's saying it's 2 squared, one's a negative, but they already kind of told us this, but we should be able to tell what this is. It's a hyperbola, right?
Yeah.
Before it gets spun, it's a hyperbola. But don't we have to go to section 10.4 to get the perfect picture of the hyperbola? Okay.
But have limitations.
Standard form, that's true, Joe, but let's start with just getting the sketch, okay? Why am I going to write this form? Why am I putting the y first? How do I know?
Figure out the center y is positive.
The y is positive, not the x, right? Do I ever have it equal to 9 in my standard form?
No.
No. So what do I need to do to that 9?
Divided by 9.
Okay. So I'm going to end up, see, Priscilla, we are kind of reviewing, but we just get to have some fun with it at the end. So we're going to divide by 9, divide by 9, divide by 9. So this is going to be y squared over 9 minus x squared over 9 equals 1. This would totally be a circle if it was plus, but it's minus. So never mind, not a circle. Where's my center?
0, 0.
You guys are tracking with that too? Is this one of the hyperbolas that's going to be this way or this way? Horizontal or vertical?
Vertical. So it's square.
Vertical because the y comes first, right? So then, let's see. How do I get my, oh, well, however, I mean, this one I could make a mistake. A is equal to 3 no matter what, but A is coming from the y squared, right? So I have 0, 0. I'm going up 1, 2, 3 to get to one vertex, and I'm going to have a zoop going up there. Then I'm going to go down 1, 2, 3 to get to the other vertex. Zoop, there he is. Don't I kind of need to know how how narrow or how broad to make this guy, to actually get him. So I have my A, I also need my B. Oh, I have my B. I mean, I don't even think I need my foci to spin it, do I? Do I need my foci? I don't think so. He's kind of like a random point. I don't think I need him. Okay. But I do need to know how wide. Do you guys remember how asymptotes? Y minus 0 equals plus or minus the y guy 3 over the x guy. Oh, wait, 3 over 3 is going to be 1. So aren't my asymptotes going to be plus or minus x? So that just means up 1 over 1, up 2 over 2, up 3. Then you guys know asymptotes, remember, they don't just go one direction, they also go the other direction, right? Yeah. Okay, so we're going to go this way too. So where's your hyperbola? Do you guys see them? In it. In it. They get closer and closer to the asymptotes, right? Wait a minute, hold on. How big am I supposed to... I'm supposed to go between -6 and 6. So 1, 2, 3, 4, 5, 6, and then 1. I'm going to put these a little closer together. 2, 3, 4, 5, 6. So I'm going to go, if you guys, I'm going to totally cheat just a little bit. And I'm going to say, hey, only go till it hits 6, which will be like right about there-ish, right guys? Yeah. It'll hit 6 about there. And then it'll hit -6 about, does that look about right? About even? Yeah. Wait, but a hyperbola doesn't just have one curve, it has, so I'm going to go to 6 this way. That was -6, and then to 6. Yeah, because you're doing what it asked, right? You have the correct center, you have the correct vertices, you have the correct curvature, and you went from where they asked you to where they asked you. Does that kind of make sense? So, yeah, but how? They could ask you hyperbolas have 2 axes. They have the transverse and the conjugate. They're saying y-axis. Which axis, maybe you guys have to connect this in your head. Which axis for this hyperbola is this y-axis? Is it the transverse or is it the conjugate?
Transverse.
Good. So what's it going to form? Maybe you memorize what it's going to form, or maybe you just figure it out. Is it an hourglass or is it 2 bowls?
2 bowls.
Because if I were to start spinning, right, they're not going to collide with each other wherever they went. If I were, I need my pencil to be longer. If I were to start spinning, right, they're just going to stay in their own little worlds, making each of their separate, I need my string, each of their separate parabolas or paraboloids. But guys, do you see how, just like with ellipses and ellipsoids, do you see how this rotation is in the figure itself? Do you see that? Yep. This rotation is in the figure itself. It can't be an hourglass. An hourglass would fill like the empty space, or would make a figure out of the empty space. This one goes inside the curvature. The other one goes outside the curvature. Dun, 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 dun. Oh, what's his name? Two sheet, because it was revolved about the transverse. Yeah, you're right. It was 2 sheet, singular. A 2 sheet hyperboloid. Now, just a hint, you can make a note of it if you want. On the test, I probably will say something like go about or revolve about. The transverse or the conjugate, I probably won't tell you X or Y. I'll instead give you the name and you have to know which one. Does that make sense? This one was nice because they said Y and you just had to figure out, is it transverse, is it conjugate to make the shape? Some of you just visualize the shape, no big deal. But on the test, I would give you like the name of the axis and you'd have to figure out which one it is. So can I show you really quickly how I grade this on a test? There would be some points. Let's just say it's 1 point for sake of argument. There would be some points for the name. There would be some points for the rotation arrow around the correct, if I give the name, around the correct axis. And then there would be points for the actual shape itself being proper. Because some of you might choose the wrong axis, do the correct rotation. Well, you deserve a little bit of points. Some of you might do the perfect shape with the perfect axis, but say the wrong name. Well, you deserve some points, right? Draw the right shape, but have it with the wrong axis. Well, you deserve some points. So this little arrow tells me which axis you are spinning it around. And then the shape that you do tells me whether or not you did it correctly, as far as I want to spin this, and maybe you show me an axis. I'm like, you didn't spin it the right way. So I'm going to want you to know the name, know how to choose an axis with a rotation arrow. If I said conjugate, you should have gone around that axis instead. And then with this rotation that you knew what shape to attach to. Does that kind of make sense?
We don't draw that arrow, we do half of the point.
Not half, 1/3. 1/3 of the point. Because without the arrow, some people, and I've seen it and I've had to take points off, would be thinking this axis and drawing that figure. And I wouldn't know unless you show me the arrow. Some people do that, Joe. Okay. So what do you guys have for homework? You have questions. You have two-dimensional lines. Lines? You can have lines in homework? Why do you have lines in homework? Hold on. We were ready for ellipses. We were ready for hyperbolas. We were ready for parabolas. And then you just spin them after you graph them based on 10-2, 10-3, 10-4 techniques. Why is there a line for the last example for today? Why is there a line? Well, how do you graph a line? We had lines in 10.1. Right? We like y equals mx plus b because in 10.1, weren't there formulas m equals tangent of theta or tangent of theta equals m2 minus m1? There were m's. We like this form. We see the m. Who's missing right now? Okay. Yeah, so b must be 0. No translation. There is a stretch. How do I graph this? B is where it hits the...
0.
Good. So it hits the origin. And then my slope? Good. 3 over 1, right? So I can go up 3 over 1. Oh, wait, but I'm not just supposed to go over 1, right? We're learning how to do these directions. I'm supposed to go over 2, right? So 4, 5, 6. Let's go over 2. Okay. And yeah, I'm also supposed to go to -2, so let's go ahead and go down 3 over 1. And let's go down 3 more over 1. Now, Joe said cone. The problem says cone, but how on earth is this a cone? It's just a line. I'm going about the y-axis, so to get your full points, you guys would be... Now, I'm probably not going to give you a cone on the test just because it's not a paraboloid, ellipsoid, hyperboloid. I'll give you all 3 of those. All 3. But for homework, why is it a cone? What happens when you spin this guy? He comes over here, he comes over here, and spinning is a rotation, right? Do you guys see why it's called a cone? If he comes over, isn't he going to come on this side? And as he comes on this side, what's he going to do?
The other side.
Yeah. There we go. But you guys kind of saw him yesterday. Didn't I show you the whole line spinning to be a cone up there? It was on the board. So maybe it's not so like, ooh, there he is. But all the conic sections come from a spun line. Okay, so homework. Here's the section. It goes through like wording and examples and all that jazz, and it has, remember, the answers to the odds in the back. But then what else do you have? You also have the actual homework exercises. Let's check out really quickly. You guys have 1, 4, 5, 7, 10, 11. Paraboloid, check. Ellipsoid, check. Hyperboloid, check. Cone, check. Triangle in parabola problem. I'm going to actually come back and I'm going to change the homework assignment Extra credit 13 was even harder than extra credit 11. I'm going to edit this really quickly and say that number 11 is an extra credit, meaning it's not going to be a have-to problem on the test. Maybe it'll be a bonus problem on the test. I'm going to save it right now so that's in there. Doop doop. And remember, you guys have the other book. Let me show you really quickly where you could find the information. Ah, look, it's a shape within a shape. And then there's a way of doing it with your calculator, basically using the max feature. And this was the harder number 13 you guys don't have to worry about. But if you want to try to do number 11, it will be extra credit on the homework, and it might even be extra credit on the test. We can talk about it as we go over questions on Friday. But right now, I actually want to get you guys your review problems. If you guys want to take out your phone, it's actually posted in Google Classroom. Here is the review. Whoa, the review's not very long. Why? Why isn't it very long? Each one could make you review everything you need for the 5 basic things on the test. We have lines and their formulas. We have parabolas and their formulas, and their clues, the foci, or the focus and the directrix. We have ellipses and their formulas, hyperbolas and their formulas, and then the spinny thing. 5 things. But those 5 things, there are a lot to do. A lot of yellow boxes to study. A lot of characteristics to be able to identify or to point out or to solve for or to use. So I didn't give you tons and tons of problems. I gave you enough on the 5 things to hopefully be like, oh yeah, I need to, oh yeah, I need to, oh yeah, that's good too. And then remember guys, this review, does it involve the other books section at all? No. So why was I giving you things like know the names, show me the rotation arrow? Because the book's not going to help you review for section 12.3 quadric surfaces. Yeah? Number 11, extra credit. We have a couple minutes left of class. You guys are getting down the review so you can work on it if you need to. Hello, sir.
I'm on a tour, so.
Oh.
How are you?
I'm doing well. They have a test on Tuesday.
Do they?
So they're writing down their review right now.
And they're going to do well? You feel confident?
I don't know. What do you guys think? They're happy though because they have a formula quiz on Monday so that you can use the formulas on the test on Tuesday. So it'll be a little bit easier. All right, you guys got it down okay? Okay, so then going back to notes, number 11 I said was extra credit. Do you want to at least get a little peek from me about how to do it? Yeah. Bonus on the test, that's not a bad idea. I mean, it's something extra. It's not something crucial. Well, we weren't very exciting, were we? Man, I had so many cool things today. They should have come in earlier. I was spinning and everything. All right, so inscribed figures is the, you don't really need it because it's extra credit, but if you want to pay attention to it, it's on the video. You can check it out and see what you think. You don't even technically need to take notes on it unless you want to. Well, because, ready? First of all, your calculator can have some issues graphing stuff, so technically it should go all the way down. I think in one of your homeworks, it said something about getting a conic section in your calculator, and you had to get y by itself with like a plus or minus square rooty thing in order to get like the top and bottom of a figure. Anyway, you could actually get this picture in your calculator, but you don't need to. What you need is just to realize this is an ellipse. And it's an ellipse with, guys, could we divide everything by 1600 if we wanted to, right? And then we could have equals 1. 1600 divided by 25, $16. Wouldn't that have 4 quarters? I think that's 64, right? Y squared. How many quarters are in 16 bucks? Yeah, 64. And then this one, yeah, because 64 times 25, so 25 times 64, x squared over 25. All that to say, I'm going to go over, the minor axis is 5, I'm going to go up, the major axis is 8. But what they're telling me is that, you know what? We've put a rectangle inside. You're like, what? Put a rectangle inside. I'm drawing a random rectangle. Now, guys, I could have drawn this rectangle to be like really tall and skinny, or I could have made him really short and wide, right? Rectangle. That's a rectangle, but which one do they want? The maximum area one. Now, could I shade this and be sure I'm pretty close? Could I say pretty sure I'm pretty close?
Yep.
Yeah, because, I mean, that area is not very big. That area is, and his area is way bigger. But did I just magically draw the perfectly right biggest rectangle?
Oh, yeah.
Really? Man, you guys have a lot of confidence. No, not necessarily. So how do I find the perfectly biggest maximum rectangle? Well, I say, you know what? Whatever rectangle I draw is going to hit at an x, which goes over a certain x value, and up a certain y value. So what would the base of my rectangle be? The whole base?
2 times up.
Well, 10 is if I'm all the way out here, but that's the skinniest, shortest, flattest rectangle. You're guessing. Can't I just say it's 2x, whatever it is? So whatever's on this side, well, it's going to be double to go on that side. And how tall is my rectangle going to be?
1 over 2.
Why?
Don't guess. Just say it's going to be the y. So wherever the rectangle hits, if it hits here, if it hits here, if it hits here, I can say the base is always double whatever the x is. The height is always the y value. Why am I doing that? Well, because I want to think about area. Area of a rectangle is base times height, which I just said is 2x times y, which I can say, oh, I know what y equals if I only got him by himself. With a little bit of algebra, I could get y is equal to the square root of, let's see, I'd have to subtract the 64 x squared. I'd have to divide the 25, but I could get y by itself, and I could go plug him in. Then I could say this is 2x times that nasty square root of 1600 minus 64x squared all over 25. Now I know it's gross to work with by hand, but do you guys realize this is something I can just throw into my graphing calculator? Right now I have an equation that can find me the area of any and all rectangles that could possibly be fit within this ellipse or half ellipse. So what are they asking for? The one that has the, so guess what's graphed right down here? I can throw this equation into my graphing calculator and say y1 equals the mess, and the mess represents area. And guess what I can do if I get my window to look appropriate? I can say, hey, I want the max. And what does my calculator find for me? Maximums. And so how do you solve these problems? You have to take your conic, you have to get y by itself, and figure out how x's and y's go into whatever equation they're saying, usually area. And then say, ha-ha, that's all the different areas of all the different rectangles hitting at all the different x's. I just need to find the max, which my calculator can do for me. And so I can say, come on, brain, this is area. You put in y1 as area. And this is your x. So I can say the max area of 40 when the rectangle hits at x equals 3.536. Bonus. Bye, guys. See you later. Yeah, work on the review and finish up, well, first, finish up other book and then the review. Come with questions and study those.